Okay, so this video is a continuation of an earlier video where we have done an analysis of a system of particles that is shown over here. In this problem, there are three particles, A, B and C. They are connected by rigid massless rods. So rigid massless rods, and they are of length L, and so these three particles form an equilateral triangle, and it is given that initially these three identical particles, by the way, of mass m, this system is rotating about its centroid, which is the center of mass, with an angular velocity of omega naught. So the center of mass O itself is static, but the whole system of particles is rotating about the point O. Since this is an equilateral triangle, the center of mass of these three identical particles will be at the centroid of the triangle, and the centroid of the triangle is at a distance h from each of these particles, and we have derived that h is equal to L over square root 3. So I would refer you to the prior part of this problem where we have done that derivation. Now, while it is turning at an arbitrary instant, the rod AC suddenly snaps, and then the motion of the three particles fundamentally change. Initially, as you can see, that these particles, each of them are turning about the point O in a circle of radius h, but once AC snaps, then the motion changes. Now the problem is interested to find out velocity conditions when these three particles will next become collinear. So the first part of this problem that we have already addressed is to find the velocities of A, B and C when these three particles become collinear. And in this configuration, B is at the center and A and C are on either side. So clearly the center of mass is coincident with the point B, or with the particle B. The center of mass does not move, obviously, because when the snapping of AC does not change the linear momentum of the center of mass of the particles, and the center of mass of the particles was static at the point O. So the point O is a static point in this case, and after AC snaps, still the center of mass will always at any instant be located at that fixed point O. So when this collinearity happens, this is one option that can happen. B exactly at O and A and C on either side. This can be an arbitrary angle. We don't care about this angle. We are not interested in finding that angle. We are more interested in finding the velocities when this collinearity happens, and this is one condition under which the collinearity happens. Note that the center of mass has to be at O, and so A, B and C can be on either side. A and C can be on either side of B, and that way it will maintain the static nature of the center of mass. And in the previous video, we have actually solved for the velocities VA, VB and VC at that instant. Now in this part of the problem, we are going to focus our attention on another potential collinearity condition, and that is when B is on one side and A and C they collide or they intersect. At that instant, VA and VC do not have to be the same, right? Because if they are different, that means they will collide. And so this can be a scenario, this can be a potential scenario, and the problem goes on to ask us to prove that this collinearity condition is not possible. So we want to show in this video that case 2 is not feasible. Now here now before we solve this problem, we need to recap a couple of things. One is that the angular momentum of the system is going to be conserved, and the initial angular momentum of these three particles is given by this expression. We had derived it in the previous video. So in the interest of time, I have not shown the derivation. Feel free to watch that video to find how the angular momentum was calculated. Similarly, the initial kinetic energy of this system of particles is also given by this expression, half m omega squared, omega naught squared L squared. And again, I'm not showing the derivation. It's pretty simple, and you can watch the other part of this problem to see how the calculations were done. So the reason we are pointing these out is because this is a problem which involves conservation of linear momentum, angular momentum, and conservation of energy. And so when we apply these, we need to make sure that we have the right expressions, and in the interest of time, I'm not deriving them. Okay, so let us consider this configuration 2. So in this configuration, what would happen is, let's say the particle B is here. Particles A and C would be coincident. So here is a mass m, here is another mass m, and here is the third mass. Now clearly here, because you have 2m on one side and m on the other side, the center of mass O is going to be at a distance of L over 3 from B and 2L over 3 from A and C. And the point O, which is the center of mass, is a static point. Its location is not changing. Also, the velocities at this instant can only be perpendicular to this rod or rods, because there are two rods here, A to B and then B to C. So let's say this velocity is VB, and we have the two velocities VA and VC. The velocities must be perpendicular to this rod, because if there were components of the velocity of these velocities along the rod, then because it's a rigid rod, the velocities would have to be the same for A, C and B, which would mean that the whole system would be moving away and the conservation of the center of mass would be violated, which is essentially saying the conservation of linear momentum would be violated. So we cannot have velocities along the rod, because again, going over it, if there were velocities of A, B and C along the rod, first of all, they must be the same. They cannot be different from each other. And that is because A to B is connected by a rigid rod and B to C is also a rigid rod. So whatever is the linear velocity in A must be the same linear velocity in B, and the same linear velocity should be in C. Okay? If that's the case, if there was non-zero linear velocities of A, B and C along the rod, I'm talking about the velocity components along the rod. If there were non-zero velocity components along the rod, then the whole system would be moving okay, and the conservation of the center of mass location would be violated, essentially, which is the conservation of linear momentum would be violated. And so there cannot be any velocities, so the only velocities that we can have for this system are velocities of A, B and C perpendicular to the rod. By the way, we should also note here, I have written the initial angular momentum and the initial kinetic energy. I should also, just for the sake of clarity, say that the linear momentum initially is equal to 0, and this can again be verified. If you take the velocities which are going to be perpendicular to these radii from O to A, B and C, then you will see that the the linear momentum is initially 0, which means that the linear momentum at any other instant will also be 0, and that's hence we are saying that there cannot be any velocities along the rod. However, there can be velocities perpendicular to the rod, okay, and for linear momentum conservation, all we have to make sure is the sum of these velocities equal to 0. So therefore, for linear momentum conservation, in config 2, we must have VA plus VB plus VC is equal to 0. Now note that my sign convention is that the velocities are being considered positive in this direction, going upwards perpendicular to the rod. And because the sum of velocities has to be 0, I'm expecting that the sum of these solutions are going to be positive and some are going to be negative, so that the sum is equal to 0. Now the angular momentum conservation will also be valid. So next we say for angular momentum conservation, in config 2, let's write the expression for the angular momentum. We can consider some I prime direction along the rod, J prime perpendicular to the rod, and K also perpendicular but going out of the page of the rod. So the angular momentum at this arbitrary configuration, whose feasibility we are trying to explore, is going to be the angular momenta of the sum of the angular momenta of these individual particles. We note that the initial angular momentum is positive. Counterclockwise angular momenta are considered to be positive. So you can see that with angular momentum conservation, so expressing the system angular momentum about O, what we get is the following. Now O is a fixed point, so we can consider O to be a fixed point. We can consider O to be the center of mass. In this case, the center of mass is not moving, so therefore in both cases we are going to get same expressions. So let us write the expression for the angular momentum considering O to be a fixed point, and so you would have the momentum of B is mvb and the moment arm is L over 3, and you can see that this angular momentum has a counterclockwise rotating sense, so it's plus k. VA is going to be negative mVA 2L over 3 is going to be the angular momentum due to the motion of A, which is the velocity VA, and it is negative because it has a clockwise turning effect. And similarly for C, it's going to be negative mVC 2L over 3K equals 0. And so this is going to give us, I'm sorry, this is not going to be equal to 0. This is going to be equal to the original angular momentum before AC snaps. So m omega naught L squared. And this was also in the k direction. So let's move on to the next page. So from here we can first of all we see that all these vectors are in the k direction, so we can cancel the unit vector k from both sides. All of the terms also have m in them, so we can cancel that as well. So we will have VB L over 3 minus VA 2L over 3 minus VC 2L over 3 is equal to omega naught L squared, which upon simplification is going to give us VB minus 2 times VA plus VC is equal to 3 omega naught L. So this is going to be our second equation. Okay, so now we have our first equation, which is the conservation of linear momentum, and we have our second equation, which represents the conservation of angular momentum, and finally we write the conservation of energy, or kinetic energy in this case, because there is no potential energy, for config 2. So the kinetic energy expression is quite simple. It is going to be half m VA squared plus, and these are the absolute values, so half m VC squared plus half m VB squared is equal to the initial kinetic energy. The initial kinetic energy is given by half m omega naught squared L squared. Okay, so this would give us VA squared plus VB squared plus VC squared is equal to omega naught squared L squared. Alright, so now it's just a matter of solving these three equations to find the values of VA, VB and VC, and from there to explore the feasibility. So from 1 we see that VA plus VC is equal to negative VB, so we can substitute for VA plus VC in 2. So from 1 and 2 we have VB minus, and VA plus VC is minus VB, so minus VB is equal to 3 omega naught L, which basically says that 3 VB is equal to 3 omega naught L, says VB is equal to omega naught L. So that is the solution for B. Now we substitute this in equation 3. We have VA squared plus VC squared plus omega squared L squared is equal to omega squared L squared. So here we have a cancellation, and essentially we have VA squared plus VC squared is equal to 0. So this is interesting because it's telling us that the sum of the square of these two velocities must be equal to 0, and this can only happen if VA and VC are individually 0. Can only happen if VA is equal to VC is equal to 0. Now if this happens, then we have a violation of the conservation of linear momentum. However, this solution gives a linear momentum of 0 plus linear momentum equation of 0 plus omega naught L plus 0 times m equals m omega naught L, which is not equal to 0. Our initial linear momentum conservation basically said that the sum of the velocities must be equal to 0. So this is violating, therefore solution violates conservation of linear momentum and therefore we can conclude that config 2 collinearity is not feasible. Alright, so we are not getting a feasible solution. So basically going back, we see that this type of collinearity where B is on one side and A and C are on the other side is not feasible because we cannot simultaneously satisfy the linear momentum conservation, angular momentum conservation, and the energy conservation equations. So that is the second part of this problem, and that basically finishes our discussion on this problem. So this problem was instrumental in showing how to apply conservation equations in a system of particles. Both linear and angular momentum conservations were applied, as well as energy conservation was applied, and the collinearity conditions were detected. It was shown that of the two possible forms of collinearity, it is only the first form that is feasible under these conservation conditions. The second form of collinearity is not feasible. That is it for this problem. Thank you so much.